Hey guys, and in this installment of chemistry, I am going to discuss acids, bases, and buffers. And as I've mentioned before, you are encouraged to follow along using my guided notes. There's the posted PowerPoint, which features links and tutorials. And further, there is even the online textbook facilitated through OpenStax, the Chemistry Second Edition. Now, as I go through presenting everything, if you find that you would benefit from kind of extended resources, many of those links are provided as an additional tool. So let's get started. We're going to talk about the definition of an acid and base, and we're going to look at kind of how they identify them because there are different varied definitions of it. We'll look at pH, pOH. We'll talk about the relative strength of acids and bases, and we'll talk about protic acids. And finally, we'll culminate everything by talking about these things called buffers. And so let's go ahead and get started by defining acids and bases based on the Bronsted-Lowry definition. And it basically states that a compound donates what's called a proton. And that proton is basically a positive H group. And so in a Bronsted-Lowry acid, it donates that proton. Now, if you look at the example of a base, according to the Bronsted-Lowry definition, it represents a compound that will accept that proton. Now, from a diagram nature standpoint, if you look at kind of these chemical formulas or structures that we have, when you're talking about a Bronsted-Lowry acid, you're looking at the behavior of what happens to an H group. And that's what we're calling our proton when we're talking about that acid or that base. We're looking at the behavior of what happens to that H group. So be conscientious of it and try to think about it and look for it in the actual chemical reactions. So let's look at another definition of acids and bases. Another definition is based on the Arrhenius definition. And in this case, an Arrhenius acid represents a compound that dissolves in water to yield hydrogen cations. Now, we know that cations are positively charged ions, and this is actually a polyatomic ion, if you will, because it features two atoms. And we recognize that ion to be called hydronium. Now, hydronium is H3O+. Now, sometimes you might see it written as just a single H+, which is just a hydrogen ion, but what's unique is that the only difference is that the hydrogen ion and hydronium are different by a water molecule. So if you picture hydronium as having that water molecule, it's the equivalent of looking at it from a hydrogen ion and water. And we'll look more at that when we start talking about this term pH, because pH is actually used to measure these hydronium ions. Now, when you look at the Arrhenius base definition, it's a compound that dissolves in water and it yields what's called hydroxide anions. And as we mentioned before, anions are negatively charged ions, and in this case, that hydroxide looks like the OH minus that's highlighted. Now, the pH range should not be completely nuanced, but if you've never heard of pH, it's a quantitative measure used to assess how acidic or basic a compound is. Now, it is a log-based function, and the range generally is limited between 0 and 14. 0 being on the low end and 14 being on the high end. Now, this is used as a function that is based on the measurement of hydronium ion concentration found in the solution. Now, the acidity and basicity of a solution can not only be measured in hydronium content, but what we'll also discover is that it will be used to be measured by its hydroxide content as well. And one interesting caveat that you want to take note of is the representation of these brackets, because in this particular presentation, when you're talking about acids and bases, the brackets suggest that you're dealing with concentration, which, if we've already looked at the previous instructional video, we're familiar with these concentration references as molarity reference. So let's look at the general function for both the pH and the pOH formula. Now, as I mentioned, we can measure the pH by measuring the hydronium ion concentration. And pH value should be a common formula that maybe we've heard of. Maybe we've heard of the terminology as it relates to pH. pOH is a little bit less popularly known, but it is still a viable measurement. In fact, it's almost like measuring how basic something is, because you measure the hydroxide ions. Now, the formulas between the two look very similar, where you have pH is equal to negative log of your hydronium concentration, and then when you look at your base, its pOH is equal to your negative log of your hydroxide concentration. And here's some key takeaways when we're looking at this general formula. To reiterate, it does measure our hydronium ion, which is the H3O+. A pH that is smaller or lower than 7 corresponds to having an acidic solution. If you have a pH that is above 7, then it corresponds to being a basic solution. And if a pH is right exactly at 7, this corresponds to a neutral solution. So when we're doing our calculations and we're looking at the pH values, we'll understand the context of whether something is regarded as acidic, basic, or neutral based on whatever that defined pH value is. Now, when you're looking at it from a pOH standpoint, you're going to have some rules that apply to deciding whether something is an acid or base or perhaps neutral. However, the rules are somewhat flipped. In fact, they are. If you think about it like this, the base is what's measured. And so because that's what's measured, a pOH value, which is less than 7, is going to be evidence that you have a basic solution. And if you have a pOH value that is above 7, that's going to indicate that you have an acidic solution. And just like it was with the pH formula, if you have a pOH or a pH that is equal to 7, that's going to correspond to a neutral solution. So when it comes down to these formulas, they are connected. And the way they are connected are in the way that their pH and their pOH value, both when added together, equal 14. So what does this lead us to conclude? Well, it tells us that if we have the pH and we're given our pOH, it should equal 14. Consequently, it should also imply that if you know your pH of a solution, you can mathematically deduce or calculate the pOH, and vice versa if you have the pOH. So, what happens when you're not trying to calculate pH, or what happens when instead of calculating for pH, you're trying to find your hydronium or your hydroxide concentration? Well, as it turns out, the reverse order of the previous equation that was mentioned is set up based on log functionality. So if we took the inverse log, we would represent the equation by saying 10 raised to the negative value, in this case of pH, would yield our hydronium concentration. And the same would be applicable if you were solving for your hydroxide concentration when giving your pOH value. They are simple math functions, and they do require a little bit of calculator practice. And as an added resource, I would highly encourage clicking the link that's provided in that PowerPoint presentation as an additional method of becoming more reinforced with understanding how the solutions break down. Later, we'll also look at a chart that kind of gives you an idea of where the hydronium and hydroxide concentration falls as it relates to something being acidic or basic. So let's go ahead and talk about one added measure, and that's the idea of pure water. When you talk about pure water, you have hydronium and hydroxide present, but they're present in equal distribution. And when an acid or base is dissolved in water, the hydronium and hydroxide are not equal to each other. So this disrupts that number. And it turns out that there is a specific constant that's associated with this value. So that if you have the concentration of your hydronium, you can mathematically deduce the hydroxide concentration. And if you have your hydroxide concentration, you can mathematically deduce your hydronium concentration. And that's based on this Kw, which is a constant, being equal to 1.0 times 10 to the negative 14. And so there's an inverse relationship between hydronium and hydroxide concentration, where as the hydronium concentration increases, the hydroxide concentration decreases, and as the hydroxide concentration increases, the hydronium concentration decreases. So let's look at that chart that I mentioned. And again, I want to reiterate that there is a wonderful resource for added benefit when it comes down to understanding the calculations regarding pH and pOH. But for all intents and purposes, basically when you're talking about classifying whether something is regarded as acidic, neutral, or basic, it is heavily dependent on the concentration of those ions. Meaning, if you have a hydronium concentration that supersedes the value of your hydroxide concentration, then that solution is mostly acidic. That means its pH is going to be less than 7. However, if your hydronium and your hydroxide concentration are equal, as is the case when you're talking about Kw, then you are going to have a neutral pH at 7. When the hydroxide concentration is greater than your hydronium, that means that your pH is going to be greater than 7, and consequently, you are dealing with a basic solution. Now, in general, you are dealing with compounds that might feature scientific notations, values for your hydronium and hydroxide concentration, so you want to be familiar with using those numbers. You also want to be familiar with using the log-based function on your calculator, which can vary depending on which calculator is being used. Now, to give you kind of an overall picture of this range and further detail this idea of an inverse relationship between hydronium and hydroxide, if you focus on the first row of an example, you notice that they're giving you hydronium as 10 raised to the 1, and they're giving you a contrasting hydroxide concentration as 10 raised to the negative 15. And in that case, you have been given a negative pH value, which we're going to assume doesn't happen classically. And then you have a pOH value that would be 15. Now, if we move down mathematically and we see that the hydronium concentration is 10 raised to the 0, or 1, and we see that our hydroxide concentration is 10 raised to the negative 14, it would yield a value where pH is 0 and a pOH that is 14. And so what we're seeing is that as one increases, the other decreases. And as one decreases, the other increases. And so when we're looking at these range, we see there's a classic case of many of the acidic materials that are associated with that range as being almost edible compounds. Whereas when you look at some of these basic compounds, you see a lot of them pertaining to being household cleaners. So now that we know that and we have that correlation between the two, let's talk about just some basic properties of acids and bases. First, acids generally carry a sour taste. There are notable examples that I'm sure you're familiar with. This includes lemons, oranges, and even grapefruit due to their citric acid. And if you want to include it, sour milk can also be considered acidic in nature because it kind of produces the lactic acid. Now, if we're talking about bases, as I highlighted before, they tend to represent many household cleaning agents, from bar soap to various drain cleaners. And it's a good idea to be familiar with some of these more common examples of acids and bases. Now, perhaps the most widely known acid and the most commercially produced is that of sulfuric acid. This material is found in automobile batteries, and can also be found in some drain cleaners. It is highly corrosive and can cause painful burns. Another example is hydrochloric acid or muriatic acid, depending on if you are familiar with it from an industrial standpoint. Now, this acid is found in the stomach lining and is heavily supportive of the digestive process of our stomachs. Phosphoric acid is a phosphate fertilizer, or used in phosphate fertilizers, and also used as an additive for food and toothpaste and as a preservative in soft drinks. Now, nitric acid is a strong oxidizing agent, and it can cause severe skin irritation when exposed to the skin, and has other actual applications such as with military explosives and other things. Now, if we're looking at some common list of bases, there are a few of those as well. The most widely known one, perhaps, is sodium hydroxide, and it is the most commonly used. It's used as a precursor in soap and many drain cleaners. Calcium hydroxide is another one, and it's made by treating lime with water, and it's used in cements. You have magnesium hydroxide, which is also milk of magnesia, and is found in food additives, toothpaste, etc. Also can be found in some antacids. And then lastly, you have ammonia, which is used as a fertilizer but has other applications. I've even heard it being used as a glass cleaner. Now, when we're talking about acids and we're talking about base, there are distinctions between whether something is regarded as a strong or weak acid or base. And part of that lies in the ability of that acid to dissociate, meaning for it to behave as an acid. If it behaves effectively as an acid 100%, then that's what makes it a strong acid. And what do I mean by behave 100%? It means during a reaction, it donates a proton or donates an H group with 100% effectiveness. Now, when you're talking about a weak acid is not as inclined to donate a proton. And so, therefore, it does not end up yielding as many reactions, if you will. Now, the other thing you want to take note of is that there are double arrows featured in these types of reactions, because if something is a weaker acid, it can actually lend to the reaction going back towards the reaction and not go towards the products. Whereas if you have a stronger acid, it will lend to yielding your products more than going back towards forming reactants. Now, when we're talking about your bases, their effectiveness is based on their ability to yield nearly 100% of hydroxide ions. If something is a weak base, it will not yield as many hydroxide ions. Very similarly to the idea of a strong acid and a weak acid. Now, to reiterate, the strong acids readily give up that proton and essentially 100% become dissociated and ready to react. However, when you're talking about a weak acid, it is not as willing to give up that proton. Now, weak bases tend to have a strong affinity for that proton that's given up. Weak bases tend to have a small affinity for protons that are given up, whereas the strong bases have a much stronger affinity and they're willing to grab hold of those donated protons. Now, the chart here depicts the relative strength of acids and bases. And one unique quality of reactions with acids and bases rests in the strength of how they behave both as an acid and a base. Now, what do I mean by that? That means that if you have something that behaves as an acid and it would be considered a stronger acid, after it donates its proton, it becomes another compound. And that compound behaves as a base. So it's kind of reciprocating behavior, both in its role as an acid and base and in its relative strength. So what does that imply? Well, it implies that if I have something that has a weak acid and it performs as a weak acid, when it participates in a reaction, it will yield a strong base. Conversely, if I have something that starts off as a strong acid, it will end up as a weak base. Now, if it's a moderate acid, somewhere in there, it's going to become a moderate base. And that's how the strength is reciprocated. Now, the other thing we want to talk about is what happens when you react certain materials together. Well, if you put a strong acid, it will react to form a weak base product, like this example provided here, which I've already said, hydronium forming your water. If you have a weak acid and it reacts to form a strong base. The example they give here is if water here becomes your strong base. And then the rows keep going in terms of indirect order. If you have a strong base, it's going to react to form a weak acid, which I highlight here. Phosphate becomes this guy. And then you have a weak base that reacts to form a strong acid, which they're giving another example of a weak base forming this one. So here are some additional representations on that chart. Same rules apply. And so if you're thinking about how they equate to one another, everything going up here increases in relative strength as an acid, and they decline in relative strength as a performing base. Now, pH can actually be measured using a number of methods, one of which those methods is pH paper. Amongst those are other ones which include litmus paper and a pH meter. Litmus paper usually features kind of a blue or red variation where red indicates acid and base indicates blue. Your pH meters give you a numerical value, and just like the pH paper in the image provided, when applied to a solution, it generates a color that can then be compared to a color scale to deduce the pH of a compound. Now, what should also be taken away from this is that some acids, even if they have the same concentration, will be stronger than others. And it has nothing to do with whether they are regarded as a strong or weak in that sense. What they're saying is that the acid that's stronger disassociates more than the weaker acid. And therefore, that's why the one on the left has a pH that is much lower. Now, there is something important to note, and that is when denoting your acid types. Some acids contain one H group that can be donated, and others feature more than one. Now, an acid that contains one ionizable hydrogen atom is going to be called monoprotic. And acids that contain more than one ionizable hydrogen atom are going to be called polyprotic. And polyprotic just means that there are more than one proton available to be ionized. Now, here are some classic examples, and it helps to be familiar with the term of these and their examples. So in this case, we have different acids that feature different numbers of hydrogen ions. We have our first example of a monoprotic acid, which features one H group that can be donated. We have another example, which is sulfuric acid, H2SO4, which is a diprotic acid because it has two protons available for donation. And then lastly, you have a triprotic acid, which is phosphoric acid, H3PO4, and it has three protons that readily donate. Now, as a general practice, you don't usually have 4 or 5 even protic acids as one of those things that you consider. So you want to be familiar with just mono, di, and triprotic acids. Now, there are 4 main types of an acid-base reaction. And for all intended purposes, an acid-base reaction is called a neutralization reaction. It is called a neutralization reaction because when you mix an acid with a base, it yields a solution that features a salt. Now, more specifically, depending on the nature of the reaction, will tell you what kind of salt you create. When you react an acid that is strong with a base that is strong, the product that you get is a neutral salt and water. Now, if you reacted just a strong acid with a weak base, you yield a salt, but in all, the solution represented is weakly acidic. Now, if you react a weak acid with a strong base, this generally yields a weakly basic solution. And again, you get a salt. And then lastly, if you react a weak acid with a weak base, this yields either an acidic or basic salt. It can fluctuate depending on whichever one is the weakest or which one is the strongest of the 2 that are weak. But in all cases, these neutralization reactions yield a salt. So now we're going to transition into a discussion about buffers. And buffers are very useful and found in a lot of biological systems. In fact, some of the more common ones that exist are examples that include our human blood as well as the stomach. And they're used to counteract any types of introduction of unwanted acids or bases. And basically the way they work is they are created by having appreciable amounts of both a weak acid and its conjugate base. Or you can have a weak base and its conjugate acid in solution. And together they make buffers. Now, buffers tend to resist the changes in pH that come with adding material to it. That's their main function. And they function based on a property led by a principle, based on a functionality of a principle called Le Chatelier's principle. And that is that if you do something to disturb the action of a reaction, the reaction does something to kind of counteract the addition. Now, a buffer is very useful because obviously if you ever have a pH difference in your blood or even a pH difference in your stomach, this can cause unwanted impact and events. And so we can use Le Chatelier's principle to kind of predict the behavior of a system based on those changes. Now, the principle itself implies that the addition of something such as heat to a reaction can reduce a reaction or have an impact on the back end, or a change in concentration can do something. And in this case, as we're talking about pH, if you add something that is deeply acidic, the reaction itself is going to do something to counteract that basic solution. Now, how does that work? Well, what happens is if hydroxide, which is base, is added to a buffer solution, the pH is going to increase only slightly, and then the acid component of the buffer is going to neutralize the hydroxide that gets added. Now, if you talk about how it works with an acid, if you add an acid proton or hydronium to a buffer solution, the pH is going to decrease only slightly, and the base component of the buffer is going to neutralize the addition of the acid proton. So therefore, your buffers serve to maintain a nearly constant pH. Now let's consider the buffer where you have kind of an acid and its weak conjugate base. Well, buffers are good at getting rid of strong acids and bases. And so if you add hydroxide or your hydronium, they're going to get consumed and not directly affect the pH. Now, as I mentioned, adding the OH gets it converted into the weak base, and then adding any hydronium is going to convert it to the weak acid. And now if you look at the image provided here, you have the pH where you have no buffer and a pH 8 with buffer. And if you look on the right of the diagram, as something is added, when acid, for instance, is added to an unbuffered solution, it's going to impact the pH and make it more acidic. That's why you see the mild color change in example B. And if you notice the system with a buffer, it features little to no change in pH, if any, based on it being able to counteract the addition of that acid proton. And so when you're talking about your buffered solutions, the concept pretty much maintains the same. If you add an acid, the buffer solution does something to offset the addition of that acid. And if you add hydroxide, which is your base, the system does something to counteract the addition of that base. And so this is an example where that change results in a small, if not minor, change in overall pH, which is the function of a buffer. This culminates the presentation on acids and bases.